Next, in our study of vectors, we're going to look at the dot product and its applications. So the dot product of two vectors results in a scalar, just a number, rather than a vector. The dot product is when we take the x values of the two vectors and multiply them and add that to the y values of the two vectors and multiply them. So for example 1, if we want to find the dot product between v and w, we take 7 times 2 plus negative 4 times negative 1. That's 18 plus 4, which is, 14 plus 4, which is 18. So pretty straightforward. If we want the dot product of v dot w, you'll start with 2 times 7 plus negative 4 times negative 1. That's 14 plus 4, which is 18 again. So you can see that v dot w is the same thing as w dot v. And then w dot w will just take the x value twice, so 2 times 2, plus the y values twice, negative 1 times negative 1, gives us 5. The properties of the dot product are pretty much the same as with multiplication. U dot v equals v dot u. U dot v plus w is the same as u dot v plus u dot w, so distribution. If you multiply a vector by a zero vector, you get 0. This one is a little bit interesting. V dot v is the magnitude of v squared. Basically, if you take v dot v, and you don't have to write this down, you're going to get, or let's do this. If you have the magnitude of v, that would be a squared plus b squared, the square root of a squared plus b squared. And then square that, then you're going to get a squared plus b squared, which would be the dot product v times v, a times a plus b times b. So that's why that works out. And then last, if you take a scalar and multiply it by a vector and then do that dot product with another vector, it's the same thing as if you find the dot product of those two vectors and then multiply by the scalar. Or if you multiply the scalar by the second vector and do the dot product with the first, it'll all be the same. An alternative formula for the dot product, which will be useful to us, is the magnitude of v times the magnitude of w times the cosine of theta. This helps us find the angle between two vectors. So to find the angle between two vectors, you can do the dot product and divide by both their magnitudes multiplied. So for example 2, we want to find the angle between these two vectors. So we're going to have cosine of theta will be v dot w over the magnitude of v times the magnitude of w. So over here, I'm just going to come to the side and find v dot w. It would be 4 times 1 plus negative 3 times 2. And that is negative 2. And then the magnitude of v would be the square root of 4 squared plus negative 3 squared. And that gives us 5. And the magnitude of W would be the square root of 1 squared plus 2 squared, or the square root of 5. So cosine of theta will be equal to negative 2 over 5 times the square root of 5. So you can find the angle between them by doing the inverse sine of negative 2 over 5 square root of 5. And just put that in your calculator, and it wants it in degrees, 100.3 degrees. Next, we're going to look at parallel and orthogonal vectors. So parallel vectors aren't necessarily on top of each other. It just means that they're either going the same direction or opposite directions. So the angles between them are either 0 or 180. That makes them parallel. Orthogonal vectors are when the angle between them is 90, just as you would expect. Orthogonal is the same thing as perpendicular. To test, let's see, is this? I don't think I wrote it down. So to test and see if vectors are parallel, then that would be if we have vector v and vector w and you find their dot product. If the dot product is 0, that tells us actually that they are orthogonal. Okay? If they're parallel, then either V dot W is equal to the magnitude of V times the magnitude of W, or V dot W, and this is in your notes. I just somehow left it off my slide. V dot W would be equal to negative the magnitude of V times the magnitude of W. So in the next example, we're going to test, are these vectors parallel? So to test and see if they are parallel, we first need to find the dot product. So the dot product would be 1.8 times negative 9 plus negative 0.3 times negative 1.5. And that is negative 16.65. Then we need to find the magnitude of each of them. So the magnitude of K would be the square root of 1.8 squared plus negative 0.03 squared. And that is 0.3 times the square root of 37. Then we find the magnitude of S. That's the square root of negative 9 squared plus negative 1.5 squared. and that is 1.5 times the square root of 37. So what we have to do is we need to test and see what the magnitude of K times the magnitude of S is. If it's either the same or opposite from the dot product, then that means our vectors are parallel. So we'll take 0.3 times the square root of 37 and multiply it by 1.5 square root of 37. And we get 16.65. That tells us, since this number and this number are the same, or in this case opposites, then these two vectors are parallel. The next example asks us, are these vectors orthogonal, parallel, or neither? So, just like before, first step is to find the dot product. So that would be 2/3 times 15 plus negative 12 times 5/6. It gives us 0. That means we're done. Because if the dot product comes back as being 0, then that means that our vectors are orthogonal. We don't have to do any further work. The vector projection. Okay. You can project one vector onto another, which will be useful to us in the future, by doing this. And we denote it as, this says, the projection of V onto W. The little W is kind of in between and below them. So the projection of V onto W is found by the dot product of V dot W divided by the magnitude of W squared times the vector W. So in example 5, we want to find the vector projection of V onto W. So the projection of V onto W will be V dot W over the magnitude of W squared times W. V dot W would be 2 times 1 plus negative 5 times negative 1. The magnitude of W squared, don't write this yet, the magnitude of W would be the square root of 1 squared plus negative 1 squared. And the magnitude of W squared gets rid of the square root and the square. Okay? So you're just left with 1 squared plus negative 1 squared down here on the bottom. And then you're going to multiply that by W, which is I minus J. Okay? Our dot product gives us, on the top, 2 plus 5 would be 7. On the bottom, 1 plus 1 is 2. Multiplied by I minus J. So that's just 7 halves I minus 7 halves J. So the projection of V onto W is the vector 7 halves I minus 7 halves J. For part B, it says, Find vectors v sub 1 and v sub 2 such that v sub 1 is parallel to w and v sub 2 is orthogonal to w such that v sub 1 plus v sub 2 equals v. Okay, so in order to do this, we've already found v sub 1 because v sub 1 and let's look at something. I think, yeah, here's the slide that should come before it. Let v and w be two non-zero vectors. V can be expressed as the sum of two orthogonal vectors, v sub 1 and v sub 2, where v sub 1 is parallel to w and v sub 2 is orthogonal to w. So we're finding two vectors, one that's parallel to w and one that's orthogonal. And that is done by finding v sub 1, which is the projection of v onto w, and v sub 2, which is v minus v sub 1. This gives you v sub 1 and v sub 2, which are the vector components of v. And this process is called the decomposition of v onto v sub 1 and v sub 2. So back to our example, we've already found v sub 1 because v sub 1 was the projection of v onto w. And we already found that to be 7/2 I minus 7/2 j. So now what we need is v sub 2. V sub 2 is v minus v sub 1. And v was 2i minus 5j. And we're going to subtract v sub 1, which was 7/2 I minus 7/2 j. Okay? So 2 minus 7/2, you can either get a common denominator and subtract, or you can put it in your calculator and change it back to a fraction, is negative 3/2 I. And negative 5 minus negative, so plus, negative 5 plus 7/2 j, negative 5 plus 7/2 is also negative 3/2. So v sub 2 is negative 3/2 I minus minus 3/2 j, and v sub 1 is 7/2 I minus 7/2 j. And those are the two vectors that we have found, such that v sub 1 is parallel to w and v sub 2 is orthogonal to w. Lastly, the definition of work. So work done by a force moving an object from A to B is the force times your vector from A to B. So the force vector times the vector from A to B. We can also write this as, and this is on your paper, the magnitude of the force times the magnitude of vector AB times the cosine of theta. So that's another way to write work, which will often be useful to us, where theta is the angle between the force and our vector AB. So for example, in example 6, it says a child pulls a wagon along level ground. It doesn't look very level, does it? By exerting a force of 20 pounds on a handle that makes an angle of 30 degrees with the horizontal. How much work is done pulling the wagon 150 feet? So, what's happening here is the work is how it's pulling it up the hill. And if it were pulling it along level ground, it'd be exerting 20 pounds of force. Also, it says how much work is done to pull it 150 feet. So 150 feet is our distance vector, or vector AB, between points A and points B. Okay? The force of the work, F, is actually the force it's being pulled down. Okay, so to find the work, we take the magnitude of the force times the magnitude of our vector AB times the cosine of the angle between it. So, I think my picture is a little bit off, but the idea is that the force is 20 pounds. So we call that 20 is the magnitude. We call that 20J because it's going down. AB is the 150 I, and of course the angle is 30 degrees. So the magnitude of the force would be the square root of 20 squared, which is basically just 20. The magnitude of vector AB would be the square root of 150 squared, or 150, times the cosine of your angle. Putting that in your calculator, you get 2,598, and our units are foot-pounds. Because we've multiplied feet times pounds, the units are foot-pounds. When you're doing these in your lab, you'll see you'll need to write your units as foot-pounds like this, and it'll tell you that in your lab. And this concludes the section on the dot product.